Matchings in graphs that are not bipartite. There are many real-life situations when finding a matching. A set of vertex disjoint edges in a non-bipartite graph is needed. Assume, for example, that a big company wants to form pairs of employees for certain assignments and wants to do it in a way that the two employees within each pair know each other. Or take a set of football teams and find pairings for this weekend so that teams that have played each other within the last 2 years do not play each other again. In these examples, we have a graph that is not necessarily bipartite, but we still want to find a set of vertex disjoint edges in it. Fortunately, there is a sufficient and necessary condition for a perfect matching to exist. If G is a graph and S is a subset of the vertex set of G, then G minus S be the graph obtained from G by deleting the elements of S and all the edges that are adjacent to them. Let CO of G minus S be the number of components of G minus S that have an odd number of vertices. Theorem 11.17 Tutte's theorem, a graph G has a perfect matching if and only if for all subsets S of the vertex set of G, the inequality CO of G minus S is less than or equal to the size of S holds. There are several proofs of this theorem. We will present one that is due to Gabor Hedjerser, 1972, and Laszlo 1975. We will need some tools for the proof of the if part. The only if part, however, is trivial. Indeed, if there is an S violating the conditions, then no perfect matching could exist. Indeed, let us assume that M is a perfect matching. Then each odd component of G minus S must contain at least one vertex M matches with a vertex of S. This would imply CO of G minus S, which is less than or equal to the size of S, contradicting our assumption. Let us call the graph G saturated non-factorizable if G has no perfect matching, but added any new H, the resulting graph does. To prove the if part of the Tutte's theorem, we need the following lemma. Lemma 11.18. If the graph G is saturated non-factorizable, and if S is the set of vertices of G that are joined to every other point of G, that is, the set of vertices of degree the size of G minus 1, then the components of G minus S are complete graphs. Proof. Let AB and BC be two adjacent edges in G minus S. To prove our statement, it suffices to show that A and C are adjacent vertices. Let us assume the contrary, that is, that A and C are not adjacent. Then there must be a vertex D in G so that BD is not in H. Indeed, otherwise B would be in S. As G is saturated non-factorizable, G union AC has a perfect matching F1. Since G itself does not have a perfect matching, this implies that AC is in F1. Similarly, G union BD has a perfect matching F2, as G itself does not have a perfect matching. F2 contains BD. Just as we did in proofs concerning matchings in bipartite graphs, let us take the symmetric difference of F1 and F2, thus consists of alternating and therefore even cycles. Let C1 be the cycle containing AC, and let C2 be the cycle containing BD. We distinguish between two cases. First, let us assume that C1 is not equal to C2. In this case, form the symmetric difference F3 equals to F1 exclusive or C1. Then we claim that F3 is a perfect matching of G. Indeed, AC is in F1 intersect C1, so AC is not in F1 exclusive or C1. On the other hand, F3 has the same number of edges of F1 and is a matching, so it is a perfect matching of G. This is a contradiction as G is saturated non-factorizable and as such has no perfect matching. B. Now let us assume that C1 is equal to C2. Traverse C1 starting at B through D until one of A and C, say A, is reached. Let the path from B to A just traversed to BP. Recall that AB is in G, and note that therefore P union AB is an alternating path, in fact a cycle, for F2. From the symmetric difference F4 equals to F2 exclusive or the union of P and AB, then we claim that F4 is a perfect matching for G. Indeed, F4 contains the same number of edges as F2, but does not contain BD, as BD is in the intersection between F2 and P union AB. This shows that F4 is a perfect matching of G, which is a contradiction. Therefore, if AB and BC are edges in G minus S, then so is AC, and the components of G minus S are complete graphs. The following theorem will characterize saturated non-factorizable graphs. Theorem 11.19. A graph G is saturated non-factorizable if and only if it has the following structure. A. Either G has an odd number of vertices and is complete, or B. G has an even number of vertices and consists of vertex disjoint complete subgraphs S0, G1, G2, and so on until Gk, so that k is equal to the size of S0 plus 2. Each Gi has an odd number of vertices, and each vertex of each Gi is connected to each vertex of S0. Proof: if G has an odd number of vertices, then it does not have a perfect matching. Therefore, only the complete graph satisfies the requirement of saturated non-factorizability, as that is the only graph to which no edge can be added. If G has an even number of vertices, then let S be defined as in lemma 11.18. Let G1, G2, and so on until Gk be the connected components of G minus S. Lemma 11.18 shows that all the Gi are complete graphs, and so is S, and by definition, each vertex of S is connected to each vertex of each Gi. Recall that G has no perfect matching. Therefore, the number of Gi with odd components must be more than the size of S. In fact, as G has an even number of vertices, the number of Gi with odd components must be at least the size of S plus 2. On the other hand, G cannot have more than the size of S plus 2 odd components. Otherwise, we could add a new edge connecting two of them. That would lead to a contradiction, because the resulting graph G1 would satisfy CO of G1 minus S, which is greater than the size of S, and would therefore have no perfect matching. Therefore, G has exactly the size of S plus 2 odd components. Finally, G has no even components, otherwise we could again add an edge connecting that component to another component without creating a perfect matching. Now we are in a position to prove Tutte's theorem. Proof of Tutte's theorem. All we have left to do is to prove the if part. Assume that G satisfies the criteria, but has no perfect matching. Add new edges to G until a graph with perfect matching is obtained. Let G' be the saturated non-factorizable graph that was created by this procedure. If G has an odd number of vertices, then choosing S, which is equals to the empty set, we see that G does not satisfy the criteria. Thus, we can assume that G has an even number of vertices. Let S' be the set of vertices of G' that are adjacent to any other vertex of G'. Theorem 11.19 then describes the structure of G' minus S'. Let H' be the set of vertices of this graph, then H is not empty, as G was not complete. It did not have a perfect matching. Moreover, H' is equals to G1 union G2 union G3 and so on union Gk, where the Gi are vertex disjoint complete subgraphs, and k is equals to the size of S' plus 2. Our last sentence shows that G' minus S' has more than the size of S'. In fact, the size of S' plus 2 components. Remove all the edges of G' minus G, that we inserted to our original graph G, then some of our components may split, but each of these odd components will give rise to at least one odd component of G minus S prime. This shows that the CO of G minus S prime is greater than the size of S prime, so G violates the condition. This contradiction completes the proof. Notes: if you want to know more about matchings, you should see reference 24 for an extensive text. One way to generalize our results concerning K-colorability is to ask the following question. Let G be a given graph on m vertices. At most, how many edges can a graph H on m vertices have, so that it does not contain a subgraph that is isomorphic to G? This leads to the area of extremal graph theory, and you can read more about that field in the identically titled book of Bella Bolabosh. For an introductory treatment to extremal combinatorics, you may consult Chapter 6 of the Reference 6. In Exercise 5, we defined the chromatic polynomial of a graph. This polynomial tells us the number of ways the property n color the vertices of a given graph G. At first sight, it seems unlikely that p of minus 1 has some direct combinatorial meaning, but amazingly it does. In fact, p of minus 1 is the number of acyclic orientations of G. That is the number of ways to turn G into a directed graph so that no directed cycles are formed. For details, see reference 36 or chapter 5 of reference 6.